welcome back for the second lecture of this week. So in the last lecture we started with lexical semantics and we defined various relations between lexical entities, and we talked about polysemy, hypernymy, meronymy, and so on. And in this lecture we will see a particular resource, Wordnet, and how it captures all these relations. So Wordnet, you can get a lot of information about Wordnet on this website. So it's an effort started at Princeton, and there are a lot of versions that have come up, and you can find out the latest version of Wordnet and also download that. And you can use that also. Once you download, you can use that in your command terminal also. So what is Wordnet? Wordnet as such is a hierarchically organized lexical database. Okay, and it's completely machine readable, so you can use that in different applications. You can call Wordnet, get various information from there. So as such, on this website you will find the Wordnet for English, but there are many other versions for other languages also built. So there are a lot of Wordnets available for European languages, and a lot of effort has happened in the last decade for building Wordnets for Indian languages, and that you can also download. Many of those versions are also available for download in free. So for that you can look at Indo Wordnet website. So there you will also find out what sort of synsets or concepts in one language are related to some other concepts in other language. So this information would be available in this Indo Wordnet and Euro Wordnet websites. So now we will focus only on the English Wordnet part in this lecture, but the methods would be easily applicable to other Wordnets that are having a very similar structure. So if we talk about English Wordnet, so there are mainly 4 different part of speech words that are present there, and what we are seeing here, how many different synsets are there for each part of speech. So there are roughly 18,000 synsets for nouns, 13,000 plus synsets for verb, and 18,000 plus synsets for adjective, and 3,000 plus for adverbs. Now, so one important thing is that when we talk about Wordnet, we talk in terms of synset. Now, what is the idea of a synset in Wordnet? So in a synset, what will happen? So various different words that have similar meanings will be stored, but a single word might have multiple meanings also. So how are both of these things taken care together? So let's take an example. So example is particular synset corresponding to chump. That is a noun that means a person who is gullible and easy to take advantage of. And suppose chump, the first sense is this particular meaning. So a word might have multiple senses. So chump first sense is this meaning, but there might be other words also that have this sense, and so this word, its ninth sense denotes this particular meaning. So I have to say that the word mark, its ninth sense is this meaning. The word fool, its second sense is this meaning. The word gull, first sense is this meaning, and similarly fall guy, and so on. So what I will do here, each word might be represented by multiple senses. So a word might have sense 1, sense 2, sense 3, sense 4, and so on. And what I will do, if suppose the third sense of word 1 and second sense of word 2 share the same meaning, I will put them in a single synset, and that is the idea of synset. Different words that share the same meaning, and by words here I will mean the lexeme, okay, or a particular sense. And for Wordnet, this list might denote what is the meaning of the word jump, although you will also find some gloss information with Wordnet. So now this figure some sort of explains what is the relation between the word form or the lemma and the synsets. So what you are seeing here, so there is a many to many relation. So that is, for example, the word note, it can go to note and 2 and bill and 3. So it denotes 2 different senses. In one sense it goes to note synset, another sense it goes to the bill synset. but this bill synset will contain node and also contains bill and some other words. Okay. So what you are seeing here, many different lemmas that share the same sense can come together in a single synset, and the same lemma for different meanings can go to different synsets, and that is captured by giving some unique identifiers to different senses of the same lemma. So I will start talking about now line 1, line 2, line 3 instead of just saying line. Okay, and each of these three will be in different synsets. So what are all the possible relations that you see in Wordnet? Here is some example. So in Wordnet you have relations like antonyms, hypernyms, hyponyms, entailment relation, synonyms, and so on. Okay, many of this we have already seen in the previous lecture. Let's see some example types of these relations. So like, what are the relations between various nouns? So the relation hypernym that we discussed. So hypernym is a relation between a concept and its super concept. Okay. So like, breakfast is a kind of meal. So I will say meal is a hypernym of breakfast. So this relation will be there in the Wordnet, where the breakfast one synset or the corresponding sense is connected to meal one by the relation of breakfast is a hypernym of meal and meal is a hypernym of breakfast. Similarly, the converse relation of hyponym, meal and lunch. Member, so faculty is so professor is a member of faculty. Has instance, composer, an instance is bash. Austin is an instance of author. Member holonym, like capital is a member of crew. Part meronym, from whole to parts, so table to leg. Part holonym, the other way around, from parts to whole, course to meal. Yes, and antonym, that is the opposite, leader and follower. So what would happen? All these relations are defined in Wordnet. You know what particular relation means, and then you can find out for a particular relation what are the different pairs, or a given pair in Wordnet, is there any relation that is defined. Similarly, there are relations between verb elements also, like hypernym, fly and travel. So fly is a kind of travel. So travel would be the hypernym for fly. Troponym, from a verb to a specific manner for that verb, like walk and stroll. So stroll is a typical manner of, or a particular manner of walking. There can be an entailment relation also from verb to the verbs that they entail, like snoring and sleeping. So I will say snore entails sleeping. So this is also a relation that is captured in Wordnet. And then there can be antonyms for the opposites. So increase and decrease, they are antonyms of each other. Further, in Wordnet you can also capture what is the complete hierarchy of a given concept. And what do I mean by hierarchy? That is, starting from the root node in Wordnet, how do you go down to that particular word? Okay, what are the different concepts that you need to pass through, and that you can find for all the different senses for a given word. And so that's why we said that Wordnet is very hierarchically organized database. So you can find out, or you can locate each concept or each subset, each synset in that complete hierarchical tree. So for example, if I see the word mouse, so I will find it has 4 senses. So for sense 1, mouse, you can find out the complete hierarchy. So mouse is a kind of rodent, kind of placental, kind of mammal, vertebrate, and so on up to animal, living thing, object, physical entity, and entity. Okay, you can go to the root of the Wordnet entity starting from this particular sense of mouse. Here is another sense of mouse, that is a computer mouse. Again, you can keep on going up the hierarchy: electronic device, device, artifact, object, physical entity, entity. And you can see where do they depart. So mouse comes under whole, then an artifact, and this mouse comes under living thing. That's where they depart in that Wordnet hierarchical tree. And this you can do for any sense, any word in the Wordnet. You can find out the complete hierarchy. Now, so as such, Wordnet will always store which two concepts are related by what relations. And suppose car and automobile occur in the same synset. If you query in Wordnet, so there is a very easy way you can query in Wordnet, and you can find out if they are part of the same synset, and you can say, okay, they are similar. But suppose two words are not part of any particular synset in Wordnet, and I want to give it a number, like to what degree are they similar? Similar to what we did in the case of distribution semantics. We found out how much two words are similar to each other by seeing how much their patterns are similar. So can I do something similar in case of Wordnet, that is given two concepts or two words, how similar they are, even if they are not part of the same synset. So by using synonymy, I can only say whether the two words are synonymous or not. But suppose I want to use a metric for word similarity or word distance. So what are the different things in Wordnet I can use? So in Wordnet there are many other relations also defined. So I can also use the fact that whether there is any other kind of relation between these two words, or do these words share a common hyponym, and so on. Also, I might have a look at the gloss of these two entries, whether their glosses are also very similar. So I'll say two words are similar if they share many different features of meanings, and the features can be captured in terms of how many relations are common, how many words are common in the gloss, and so on. Now, one thing that we must keep in mind when we are talking about establishing relation between different entities in Wordnet, we are talking about relation between different senses and not the words. Okay, because a word might have multiple senses, and the relation that is there in one sense of word one and one sense of another word may not be there in the other senses. So for example, here, for example, there is a verb bank. This is sense one. This is in the sense of, you can say, in the economics, and sense two is like river bank. Okay, and then I have another word like fund. Okay, and there is S1, that is for economy. So I will say that this sense one of bank is connected to this particular sense of fund, but I cannot say that this is connected to fund. This is not true. So I cannot say that bank is connected to fund. Saying that will not be correct. What I will say, sense one of bank is connected to sense one of fund. So we will talk about relations between senses of words and not word directly, although we will try to extend it later to the words. Okay. So instead of saying bank is like fund, I will say something like bank 1 is similar to fund 3, suppose that is the third sense of fund, and bank 2 is similar to slope 5, the fifth sense of slope, and so on. Now we will also compute similarity over words and senses both. So let us see how do we do that by using the Wordnet hierarchy and any other information that we have. So now this is something that we have talked about earlier, that if I want to find out similarity between words, there are two very popular methods. One is by using distribution algorithms, and that we discussed in detail in the last week, that I can find out the distribution patterns of two words and compare those. But if I want to use a lexical resource like Wordnet, so here can I use the idea that some words are more near in the Wordnet hierarchy than others. So if two words are near in the hierarchy, I might say they are similar. If they are very far apart in the hierarchy, they might be different. So can I use this idea to establish if two words are similar by using the Wordnet resource? And we will now see lot of such methods of doing that. So as such I can use any relations like meronym, hyponym, troponym, glossage, examples. Yes, but in particular the thesaurus based methods that we have, they mainly use the EJ hierarchy tree, the hyponym relation tree. Sometimes you will also use the glossage of the words. So we will start by seeing some examples or some particular methods that try to use the hierarchy, Wordnet hierarchy, to capture the similarity between the words, and then we will also see a particular method that uses the glossage of the different synsets to capture their similarity. Now, so one thing that you might have seen or have understood by now, that by using all these methods we are not capturing the synonymy as such. We are not saying that we are finding two words that are very, very similar. What we are finding is that two words that are related or are used in similar sort of context and topic. So like if I take car and bicycle, they are quite similar, but car and gasoline, they might be related but not similar. So by these methods car and gasoline might come closer, but all it means is that they are related. They may not be exactly similar. So now coming to the methods to capturing similarity across words. So what is the first idea? First idea is to use the path between two words in the hypernym graph. And what can be a simple measure? I will say that two words are similar if the path that connects the two words in that hierarchy tree is small. Okay. So two words are similar if they are nearby in the hypernym graph, and to give a formal measure or quantity to that, I can define the path length between two concepts. So path length between two concepts, what will be that? That is the number of edges in the shortest path in my graph between senses C1 and C2. So what is the length of the shortest path that connects C1 and C2 in my whole graph? Now once I have found this path length, how do I use that to compute the similarity between these two concepts? So I teach if path length is large, they are less similar. If path length is small, they are very, very similar. So my similarity should be inversely proportional to the path length. So one measure can be 1 divided by 1 plus path length, and this is one simple measure that is used. The path similarity between two concepts is 1 divided by 1 plus path length of C1 and C2. So that's how we can find out the relation between two senses. So now suppose I want to extend that to find the similarity between two words. So one way is to find out similarity between all the senses and take an average, but a more commonly accepted measure is find out similarity between all the possible pairs of senses between the two words and take the maximum. Okay. So what do I mean by that? Suppose I have word 1, word 2, that is sense S11, S12, S13, and this is senses S21, S22. Okay. So by using this measure, I can find similarity between any two pairs, S11 and S22. What is the similarity? Similarly, I can do for all these pairs. Now, how do I establish similarity between W and W2? So I teach the similarity is the maximum value of similarity between S1I and S2J. You take any sense for the first word, any sense for the second word, whatever is the maximum similarity between a pair gives me the maximum similarity or the similarity between these two words. So that is a very simple way in which I can extend all these ideas to word similarity. So in whatever we will see for the next methods, we will also always talk about similarity between senses and extend it for similarity between words. So I will say similarity between words W and W2 is nothing but the maximum similarity between any of the senses of word 1 and word 2. So let's take an example that what will this pathway similarity look like. So this is my Wordnet hypernym graph. So not all the nodes are shown, only if very few nodes are shown. So you are starting with entity, abstraction, major, standard. Although with entity there will be other concepts here. Then you are coming to a particular branch where you have medium of exchange, currency, coinage, coin, nickel, and so on. Now I want to find out similarity across two different concepts. So what is similarity between nickel and coin? So I'll say what is the path length, path that connects nickel and coin. What is the length of this path? So here the length is only 1. So similarity between these two concepts will be 1 divided by 1 plus 1, so 0.5. And what is the similarity between nickel and dime? It will be 1 divided by 1 plus path length, and path length is 2, so it will be 0.33. And if you see a nickel and a very different concept like richer scale, so here you will find similarity is 0.125 because the path length is 7. So like that I can capture the similarity between two concepts by using the path length. Now there is another similarity measure along the same lines. So this is called LC similarity. So what it says, the similarity between two concepts is minus log of path length divided by 2d. Okay, so this is just a different function over path length. So earlier we had a function 1 divided by 1 plus x. Now they have function minus log x divided by 2d. Okay, and what is d here? D is the maximum depth in my hierarchy. Okay, so starting from the root node, what is the maximum depth of my hierarchy for any of the leaf node? And this helps in that this path length will always be less than or equal to 2d, and this will give me a similarity between these two concepts. So so what is the problem with this LC similarity or the previous similarity that we have seen? So what they are saying, for any two concepts, find out the path length, and the similarity is nothing but a function of path length. If path length increases, the similarity decreases. But one problem with these approaches is that any two pairs of concepts, if the path length is same, the similarity will be the same, irrespective of wherever they occur in the tree. So let us just go back to the previous tree. So what these approaches will say, so what is similarity between coin and nickel? The path length is 1, similarity is 1 divided by 1 plus 1, that is 0.5. But what would be the similarity between entity and abstraction? Their path length is also 1, so their similarity will also become 1 divided by 1 plus 1, so that is 0.5. But ideally what would we want? Do we want the similarity of entity and abstraction to be the same as between coin and nickel? So if you think about it, as we are going down in the hierarchy, we are moving to very, very specific concepts. So when we are moving to specific concepts, the same path length should amount to a higher similarity now that it was doing earlier. So entity and abstraction, this similarity should be much lower than this similarity. This similarity should be very, very high. But these methods as of now do not capture this idea. So they will have this path length to contribute same way as this path length. So now can we do something different so that here the similarity becomes high, but here similarity becomes low? So we want a metric that lets us assign different lengths to different edges. So what is the idea that we will be using? And for that we use the idea of concept probability model. And what is this? So in the Wordnet, whatever concepts we are seeing, we will assign them a probability. So what is the probability with which I see this concept in a corpus? Now idea would be whatever I am seeing in my corpus is an entity, because it's part of that tree, so where entity is the root. So whatever word is there in that tree is an entity. So in the other word, whatever word I am seeing in a corpus is an entity. But it may not be an abstraction. So there will be some words that are abstraction, some words that are not. So what I will do, whenever I encounter a word, I'll find out what are all the concepts to which it contributes, and I will add a count to all these concepts. And finally, I'll convert them to probability values. So what would happen? The root node will get a probability of 1, because everything that I see is an entity. But as you go down, these values will keep on decreasing. I'll use this idea, okay, to convert them into log values, and then taking the difference between two values as the path length, okay, and that can be converted to finding the similarity between two synsets. So let us say PC is the probability that a randomly selected word in a corpus is an instance of C. So what would happen? Probability of root is 1, and the lower a node in the hierarchy, the lower is its probability. And how can we estimate these probabilities? We count something called concept activations in the corpus. So what would happen? Whenever I encounter a dime, I'll also increment count for coin, currency, standard, etc. So what is the idea? So I have a Wordnet hierarchy tree starting from root, that is my entity, and going down. So what would happen? Suppose this is my word X. Whenever I encounter this word X in my corpus, I increment its count by 1 and all its parents, because whenever I am encountering this concept, I am also encountering this concept, and so on. So what would happen? Whatever I encounter, I always add 1 to the root, okay, but only to its parents. So when I do that, root will have, so all the counts will be added to root, and I can find the probability by dividing everything by the count of root. So suppose I do that on my corpus. This is one example. So here you can see there are 1.9 million roughly instances overall, because entity has been always appended with 1. But the numbers are different. So dime and nickel has only 8 and 10, coin has 1,108. Okay, so you can see that we are not showing the whole tree. That's why there will be some other branches of coin also that are not here. So now once I have got these counts, I now obtain the probability values by dividing everything by this number. So this will be my concept probability. Now how do I use this concept probability to define my edge weights? So what I will do, I will convert them in some information value. What is the information content of each concept? And the information content can be directly obtained by the probability values by using minus log probability. Okay, the idea is that if the probability of something is very high, it does not have much information, but the probability is low, it contains a lot of information. So I use the information content of a concept as a minus logarithm of the probability of that concept. So I can do that for all the concepts, and I can also define what is my lowest common subsumer. That is, if I take two nodes or two concepts C1 and C2, the lowest common subsumer is the lowest node in the hierarchy that subsumes both the nodes, or what is the lowest node in the tree where these two concepts meet. And now we will see how we can use that for computing a similarity between concepts. So these, by using from the probability, if I take minus log probability, the other different numbers I will get. So minus log 1 becomes 0 for entity 0, then 0.596 and so on. Now what is something that you are seeing here? So as you are going down, these numbers are increasing. So one simple way of capturing similarity between two words is by seeing what is the lowest common subsumer and what is the information content of that. So nickel and dime, what is the similarity? Path length is 2, but the lowest common subsumer, that is coin, has an information content of 7.455. On the other hand, if I take these two concepts, medium of exchange and scale, their lowest common subsumer standard has an information content of 6.11. So immediately you can see this can be said to have a higher similarity than this pair. Okay. So what are the formal methods by which we can capture this? So one is rational similarity. So that says how similar two words are depends on how much they have in common. So that is, find out their lowest common subsumer and find out the information content of that, and that will denote the similarity between these two concepts. So it measures the commonality by the information content of the lowest common subsumer. Okay. So like here, nickel and dime, the similarity would be the information content of the LCS, that is coin. So similarity between them is 7.455. Now nickel and money, similarity would be information content of their LCS, that is medium of exchange. So it would be 6.255 and so on. Okay. So now immediately you can see that as you keep on going up in the hierarchy, the similarity will be decreasing. So it will be highest when you are seeing the leaf nodes, but if you keep on going up, the similarity will decrease. So this is capturing what you wanted to do, but still there is one problem here. So can you find out what is the problem? So one problem here is, if I find a similarity between coinage and money, this will be same as the similarity between coinage and budget. Yes, because their LCS is the same. So here what is being captured is that how much information they share, but what is not being captured is how much information they do not share or how much they are different. So we have a different measure for capturing how much information they do not share, and this is called Lin similarity. So it says that this measure is not about just commonalities, we also have to capture the differences. So the more information they share, the more similar they are, but the more information they do not share, the less similar they should be. Okay. So accordingly, the Lin similarity between two concepts is defined as 2 times logarithm of, or 2 times information content of the LCS divided by information content of the concept 1 plus information content of the concept 2. So by doing that, what would happen? Now if I take the similarity between coinage and money, this would be 6.255 times 2 divided by 7.419 plus 8.042, and if I take the similarity between coinage and budget, it will have a term of 10.423 in the denominator instead of 8.042. So immediately this similarity will become lower than this similarity. So Lin similarity is a much more well accepted measure than the previous measure that we have seen, the rational similarity. There are some variations here. So for example, the JC similarity. So what they say in JC similarity, find out or give a value to each edge, that is the distance between two concepts, and this would be the information content of the concept minus the information content of the hypernym, and I can define the distance between two concepts as their distance. So how do I go from one concept to its LCS and second concept to its LCS, and I just add the distances, and I compute similarity by taking the inverse of this distance. So what am I doing here? I am having different nodes in my hierarchy. Yes, and suppose that you have already found what is their information content. Okay. So what do you do in the case of rational similarity? In rational similarity, this C1, C2, C3, and this is C0. In rational similarity, the similarity of C1 and C3 is nothing but the information content of C0. So as per Resnick, similarity of C1, C3 is IC C0. Okay. as per Lin similarity, this would be 2 times information content of C0 divided by information content of C1 plus information content of C3. Now, in JC similarity, what you would do, you would count, you would find out the distance. This distance is nothing but C1 minus C0, and this distance is C3 minus C0. So, for JC similarity, it will be C1 minus C0 plus C3 minus C0. This is the distance between the two concepts, and similarity would be 1 divided by that. Okay, and that's what is written here. Information content of C1 plus information content of C2 minus 2 times information content of the LC of the two, and that's what you can see here. IC of C1, IC of C3 minus 2 times IC of their LCs. So, I hope by this example you understand what is the difference between resonance similarity, Lin similarity, and JC similarity. And among these, Lin similarity is very popular. Okay, so I hope it is clear that how do you apply these 3 different similarity measures. So, here in an example, that if you use the JC similarity, what is the different values that you will obtain among different concepts. So, I will encourage that you try and find out that, say suppose between nickel and richer scale or between nickel and coin, can you obtain the same values by applying the formulas. So, now I will also talk about briefly the other approach for computing similarity between 2 different concepts in Wordnet. So, till now we have only used the hierarchy tree in Wordnet, and I am saying 2 words are similar if they are nearby in the hierarchy tree or some other formulation, and that we have seen some examples. Now, suppose I want to use their glossage, the way the different concepts are defined in Wordnet for computing similarity. So, there is a very simple algorithm called Lexical algorithm. Also have an extended Lexic version that is used for that. And what is the idea? 2 concepts are similar if their glossage contain similar words. So, I have the word drawing paper defined as paper that is specially prepared for use in drafting, and decal, the art of transferring designs from a specially prepared paper to a wood or glass or metal surface. I want to find out how similar they are. So, what I will do, I will see how many words are common there. So, as such you are seeing there are 3 words that are common: paper, especially, and prepared, okay, that occur in both the glossage. So, what algorithm does is that it counts how many n-grams are common. So, n-gram in the sense of unigram, bigram, and trigram, and so on. So, you will see that this bigram specially prepared is common to both the glossage, and this unigram paper is common. So, whenever an n-gram is common, it adds a score of n square, so that a higher weight is given for a commonality of a bigram, trigram, and so on. So, in this case, what will be the similarity? 1 bigram is common, so 2 square, and 1 unigram is common, 1 square. So, similarity would be 2 square plus 1 square, 5. Okay, 1 plus 4, 5, and that is the simple idea of using Lexical algorithm. Now, so we have talked about what are the different relations we can capture using Wordnet, and we have also seen how we can find out similarity across 2 words, and that looks like very simple method once the Wordnet tree is given. And you might also wonder, this might be a better method of capturing similarity than distribution similarity, okay, because I have a manually created thesaurus. I know which of the words occur where in the tree. I can simply use the distance or some measure to find out how similar they are. But there is one inherent problem in using Wordnet for any of the tasks. So, can you think of what is the problem? So let me give you the hint. If you want to capture similarity across senses, Wordnet is very good. It can capture the similarity between senses very nicely. But if you want to capture similarity between words, that is very difficult. Now, when we encounter a natural language, we only encounter the words, and when we see the words, we do not know what are the senses that are being used. So I cannot directly apply Wordnet there because I do not know the sense. I can only do an approximation where I can find out, okay, I am assuming this word corresponds to, or I am applying the methods I used for sensage for the words. Okay, this will be an approximation, and it works sometimes, but does not work some other times. So to be able to apply Wordnet, to be able to use Wordnet, one important problem that we have to deal with is I need to find out if a word is used in a particular sentence, what is the Wordnet sense that has been used for that. Okay, and that is a difficult problem that we will try to address. But this problem is very, very common, and we will just take a very simple example for that. So we see a very easy sentence. I saw a man who is 98 years old and can still walk and tell jokes. Yes, it's a very simple sentence. Now for the simple sentence, what do you think? Are there many different senses of this word or this whole sentence, or there is only one interpretation? So when we hear this term, this sentence, we have only one interpretation in mind. But in Wordnet, what are the different senses of individual words? So let us see. So if I go to Wordnet, the word saw has 25 senses, man has 11 senses, ears has 4, jokes has 4, tell has 8, and so on. So now if you combine all these together, there are as a 67 million plus senses that are possible for this sentence. This might look like a very extreme case, but you might have examples where there are multiple interpretations for the same sentence, and different words can occur in multiple senses. So my problem is, if there are so many senses, how do I find out what exact sense in Wordnet is being used? And that's where we talk about the problem of word sense disambiguation. Among the many possibilities, disambiguate the particular sense of the word, and that we will start in the next lecture. Thank you.